Okay. 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 So today's speaker is Yossi Avron from Technion in Haifa, and he's going to talk about the Mermin-Peres game. I don't know. I guess in his version, there is a referee. In other versions, I've seen somebody else. But anyway, I think Yossi, you can get started now. Okay.
Okay. Can you hear me, or am I muted?
I can hear you.
Okay, great. So thanks, Joel, for inviting me, and thanks, everybody. I'm going to tell you today about a quantum game, which is known as the Mermin-Peres game. And the game has a classical and a quantum version. And the purpose of the game is to show that once parties are allowed to use entangled quantum states, they have an advantage in playing the game. So I'll start by describing the classical version of the game, where the parties do not use any quantum information, any quantum states, or any entanglement. And then I'll go on to describe the entanglement. And as we shall see, this will increase the winning probability. So this is how the game works. It's a cooperative game of Alice and Bob. So Alice and Bob want to have a joint strategy, and they want to beat the casino. The casino will pose challenges to Alice and Bob, which they will have to address. And if they address them successfully, they win the game. And if they do not, they lose the game. The catch is going to be that even though Alice and Bob can cooperate, once they decide on a strategy, they cannot communicate. So it's a game of two cooperating but non-communicating parties. And please interrupt me at any point if I'm not clear. So let me explain what are the rules of the game, which Alice and Bob know. So there is a square, which is shown here. It's a 3x3 square. Can you see the spotlight, I hope?
Yes.
Yes. So it's a 3x3 square. And after Alice and Bob decide on whatever strategy they want to use, each of them is put in a different room, and they have no telephone, they have nothing to go, they have no internet, they can't communicate. And the casino tells Alice to fill a row in the table. And she needs to fill the row with numbers that are either plus or minus 1. And she has to fill the row in such a way that the product of these three numbers she put in is plus 1. So this is shown here in the picture, and it's written here. So that's what she has to do. Now, Alice has no idea what row she would be given, and the row is given randomly. So the casino decides, in this case, to put the second row, but it could tell Alice to fill the first row or the third row. Now, similarly, the casino tells Bob to fill a column. And again, he has to fill the column with either plus 1 or minus 1. And the constraint is that the product of the numbers in his column has to be minus 1. Now, so this is a constraint on how Alice and Bob are supposed to fill a random row or a random column. And these random rows and columns are picked uniformly. So any row or any column can arise. Now,
Yossi?
Yeah.
Is Bob told which row Alice had to fill out?
No, no, they have no idea which row Alice doesn't know what column Bob is given, and Bob doesn't know which row Alice is given. Now, at the moment, so far, this is a trivial game to win because they can decide that whatever row Alice is given, she will always put +1, and whatever column Bob is given, he will put -1. So to make the game interesting and non-trivial, here is now a second constraint. The constraint is the following. It makes the game hard. The constraint is that the intersect of, say, Bob's column with Alice's row is such...
Sorry, Yossi, you
Yeah.
did not define what is winning.
Yes, I'll tell you now what is winning. Alice and Bob will win the game if they satisfy the constraint in the previous transparency, so that product of the entries in a row is +1 for Alice and -1 for Bob. But there is now additional constraint that the row of Alice and the column of Bob intersect in a square, which here is shown in green. And the constraint is that in this square, they must be consistent. So, for example, this is a winning case where Alice put 1, 1, 1, and Bob puts 1, 1, and -1. But they only win if they agree on the intersect. Now, the question is now, what could Alice and Bob, what kind of strategy Alice and Bob could have so as to win the game? In order for Alice and Bob to win the game, they must agree on a table, because they don't know a priori which square is going to be the intersect. So the intersect could be the middle square is here, but it could be also be this square or that or any other square. So they must agree on a common table that they are going to use so that they will always agree on the intersect. But as I will now show you, and I think it's quite easy to see, this is not possible. You cannot agree on a common table that will satisfy all the constraints. And here is a way to see this. If I could fill the table if I could agree on a table satisfying the constraint, then the product of all entries in the table, according to Alice, must be +1 because it's the product of all 3 rows. But according to Bob, it's the product of all 3 columns, which is -1. So because of this, it is just not possible to have a table which will satisfy the 2 constraints and that Alice and Bob could agree on. So this is because multiplication of numbers is commutative. So if I multiply the columns, the rows, or I multiply the columns, I would get the same answer. Am I clear so far? Have I lost anybody?
No, that's fine.
That's fine. Good.
So, but you say, aside from this, they are not told actually which column Bob is given, or
That's right.
Which row is given.
Yes.
Okay.
Yes. If they were told, they could make many tables that they would use according to which rows and which columns are given, but they are not told. So they have to agree on a common table, and I just showed you that there is no such table. So what they can do is agree on a table that would win with high probability. So here is an example of what could be a high probability. Here is a table that would allow Alice and Bob to win 8 out of 9 times. So let me show you how to construct such a table. So take the top 2x2 square, which I'm now showing, and fill it any way you want. For example, I fill it with 1, 1, 1, 1. And now Alice will complete the first row to satisfy the constraint. So she would put here 1, and she would complete the second row to satisfy her constraint. She put here 1. And Bob would satisfy the constraint by filling this column to satisfy the constraint. So he would put -1 here, and he would put -1 here. Now, as I told you, there is no way to fill the entire table. And indeed, if you try to see what would happen in the red square, there is a conflict. Alice would want to put a sign which is a plus, and Bob would want to put here a sign minus. So they can agree on a table, and they will give up on 8 squares out of 9, and they would give up on the 9th square, this on the red square. And this would mean that they would win the game 8 out of 9 times. So are you with me?
I am. I don't know. Anybody else has any questions or comments?
Anybody
I have a
can comment.
question. Isn't it analogous or similar to the so-called sinkhorn algorithm?
I didn't understand the question.
Is
Can
it
you ask it?
analogous to the so-called sinkhorn algorithm that does alternates between rows and columns operations?
I still didn't get the question. Can you repeat the question? What
Okay,
is the...
there is an algorithm
Yeah.
called sinkhorn, S-I-N-K-H-O-R-N. Sinkhorn, they compute the sinkhorn limit. That is very reminiscent of what you did, where you alternate between operating on rows and columns, and very fast it gets what you want.
So I don't know about this this algorithm, and so I don't want to take a stand, but I think I convinced you that there is just no way to fill the table, and I also showed to you that you can agree on 8
No, I'm not
out
saying
of
there's
9.
a way, but I think maybe you want to maximize the probability. So maybe
I'll make a comment about random strategy. At the moment, I want to describe a sure strategy, and later I'll comment about what about making a random strategy. But so let's leave it for now. So here is a statement about the random strategy. If you would, you can ask, can I do better by not having a fixed table, but picking from a collection of such tables, say each of them wins 8 out of 9. And then you can see by a simple argument of convexity that the winning probability, if you make a random strategy, then here is the probability of picking a given strategy, but the probability for winning at any given strategy is at most 8 over 9. So the winning strategy, even if you allow yourself randomness, does not improve. So I think this addresses the question that you perhaps asked. Okay, so now that I showed to you that it's not possible to win this game always with any classical strategy, I want to describe the quantum version of the game. And the quantum version of the game is going to be such that if you allow Alice and Bob to use entangled quantum states, then they can win the game always with probability 1. So in every round, they will beat the casino. And so how is the quantum game different from the classical game? Say when the Alice and Bob make their strategy, they are allowed to prepare a quantum state. In fact, as we shall see, they will prepare a quantum state of 4 qubits, and Alice will take qubits to her room, and Bob will take 2 qubits to his room, and the qubits will be in a state which is entangled in a way that I will explain later. And then in their individual rooms, although they cannot communicate, Alice and Bob are allowed to do measurements on the 2 qubits. And now the strategy for winning the game would be now that Alice and Bob will fill the table that we saw before, but they will not fill it with numbers. Instead, they will fill the numbers, the table, with observables. And I'll tell you which observables they will fill them. So the observables, I denote them here. B11 will be the measurement that Alice will make if she is given, say, this row. So she will measure B11, she will measure B12, and she will measure B13 on her qubits. And if Bob is given, say, the first column, he will measure B11, B21, and B31 on his qubit. And the measurement are going to be such that each observable here, which is denoted by B, is a binary observable. So the result of a measurement will always be either +1 or -1. And therefore, Alice will, since she will measure these 3 observables, B11, B12, B13, she will fill her row with 1 and -1 randomly according to whatever measurement result she gets. And similarly, Bob will fill his column. And the miracle that is going to occur is like this, that the constraint that Alice has, that the product of entries in a row must be 1, will be satisfied. The constraint that the entries in a column for Bob has to be -1 will also be satisfied. And in addition, the common square for Alice and Bob, they will both measure the same, they will get the same result for their measurement. So this is the miracle that is going to happen in quantum mechanics, and this will be independent of which row and which column Alice and Bob are given. And in the following slides, I shall describe how this miracle occurs. But am I clear so far? Are there questions?
I guess you're going to use Einstein-Rosen-Podolsky kind of things.
It's going to be Einstein-Rosen-Podolsky in the sense that I'm going to use entangled states, and moreover, it will be states which are very reminiscent of the maximally entangled states used in Einstein-Podolsky and Rosen. So there will be the special correlations that can occur in quantum mechanics will play a role in winning this game. Okay, can I move forward, or I've lost everybody by now?
Go ahead.
Okay, so let's.
Is it correct
Yes.
to say that this is generalization of quantum teleportation problem?
No, it's not going to be teleportation, because first of all, in teleportation, Alice and Bob are allowed to communicate. And
okay.
we are not going to transfer. We are not going to transfer an unknown state from Alice to Bob, but there will be a miracle which happens in the Einstein-Podolsky-Rosen thing, that the measurement of Alice and the measurement of Bob are strongly correlated. So this will be responsible for the fact that they will get the same response on the joint square. So first let me describe how to build this table of observables. So as I said, each observable is a self-adjoint operator, and the self-adjoint operator is such that it squares to 1, and the trace of this of any of these Bij is 0. This means that the spectrum of B is either +1 or -1, and therefore measurement of any of these observable, B11, B12, etc., the measurement of any one of them will give me a response which is either +1 or -1. Now, we will fill the table in such a way that the product of the observable in every row is +1, but now the +1 is one as an observable, as a matrix. And so the product of these, the observables in this row is 1, and the product of the observable in this row is 1. So in every row, the product is 1, and in every column, the product is -1. So this is a reflection of the constraint that we saw previously for numbers. But now, since we are decorating this table not with numbers, but with operators, the product of operator is non-commutative. So the fact that the product of these ones here give 1 and the product of these -1s here give -1 is no concern, because the product of operators is non-commutative. Now, in addition, we will need these observables to have the following property. We want Alice to be able to measure the 3 observables in a row, which means that we need B11 to commute with B12 and to commute with B13, and so that the product would be +1, etc. And similarly for the second row and for the third row. And similarly for Bob, since Bob has to measure the 3 observable in a column, we want the observable in each column to commute. So observables in rows and columns will commute, but in general, say the observable B31 and B22 will need not commute, and they will not commute. So here is the summary of what I said in a formula. Observables in same row commute, observables in same column commute, and the product of observable in every row should be +1, and the observables in every column should be -1, and each observable should have spectrum which is either +1 or -1. So now the question is, can I make such a table? Can I fill this table subject to these rules? And good. And such a table indeed exists, and it will exist where every one of these observable B is made of a product of 2 Pauli matrices. And I will build this. I'll be explicit in a minute. And so to remind those of us who may have forgotten what Pauli matrices are. So sigma X is the matrix 0, 1, 1, 0. Sigma 1 is 0 minus I 0, and sigma Z is the diagonal 1 minus 1. And I call sigma 0 the identity. So these are the Pauli matrices. And the tensor product of 2 Pauli matrices is a 4x4 matrix. Now, it's a property of Pauli matrices that every 2 Pauli matrices, which are not, if none of them is the identity, the anti-commutator is proportional to twice delta JK. They form a Clifford algebra. The anti-commutator of 2 Pauli matrices is 2 delta JK, but the commutator of product of 2 Pauli matrices is 0. This is because J and K anti-commute, and K and J anti-commute, and therefore the product of such of this form commutes. So this was just a reminder about Pauli matrices. I hope this was not too bad for you, but Okay, and now the claim is the following, that here is a way of building a table that will satisfy all the constraints I mentioned before. So, for example, in this square, we put the identity times tensor product with Pauli matrix sigma z. In this entry, we put minus sigma x, tensor sigma x. And now you can check, it's not so bad. We can try to check it together if you want. The product of the matrices in every row is the identity. For example, if I multiply these three, sigma 0, sigma x, since sigma x squared is the identity, the first term is going to give me the identity. Similarly, sigma z, sigma 0, sigma z is again sigma z squared, which is the identity. And it's also easy to see that this pair of matrices commute. So matrices in every row, the matrices commute. And similarly, matrices in every column commute. And the product of entries in every column would be -1. And it's actually quite easy to build such a table if you ever need to build one. We do it like we did in the +-1. We first take this small 2x2 square and we fill it with a tensor product of Pauli matrices so that the two Pauli matrices in every column commute. Here I achieved it cheaply by putting the identity here and putting the identity here, so it is evident that these two matrices commute. And once you fill this square with matrices that commute in a row and commute in a column, then you fill the rest of the square by the constraint. You wanted the product of this and this times this would be +1, so this fixes this entry. And then Bob fills the matrices in the remaining by his constraint on a column, which is -1. And the miracle that occurs is that now Alice and Bob actually agree on what is happening in the red square. Previously, they did not agree, but now they do agree. And the main reason is that previously the disagreement came because multiplication of numbers was commutative, but multiplication of Pauli matrices is not commutative.
Just so
yeah,
inside each square, you have 4x4.
Mm-hmm.
And then
Indeed.
And the product is also a 4x4.
So a tensor product of two Pauli matrices is a matrix which is a 4x4 matrix. That's correct. But you could also think of it like this, that the fact that I have two Pauli matrices means that Alice and Bob can make two measurements on 2 qubits. So if Alice has at her disposal 2 qubits, she can measure something on the first qubit and she can measure something else on the second qubit. Was this helpful?
But what happens when you take the product of all three of them? What do you get in a row?
In a row, shall we do an example? Let's multiply the first row, right? So just look first at the first entry. So here is sigma 0 multiplied by sigma x. Sigma 0 is the identity, so the product is sigma x. Now multiply sigma x by this sigma x, so it's sigma x squared. So we got the first entry is the identity. Now let's check the second entry. Sigma z times sigma 0 is the identity, so it's sigma z. And sigma z times sigma z is sigma z squared, which is the identity. So the product of all three is the identity tensor, the identity, which is the identity.
Which is what?
The identity. So the product of the three entries in a row is the identity matrix.
4x4 identity
The
matrix?
4x4 identity matrix, right?
Okay, that was a question.
Yes, and the product of the columns is a 4x4 minus the identity.
Okay,
Okay, so now what Alice and Bob agree on is a table of what measurement they are going to perform. So for example, if Alice is given the first row, she knows she's supposed to make these measurements. Measure enough here, she doesn't need to measure on the first qubit, but she needs to measure sigma z on the second qubit. And here she needs to measure sigma x on the first qubit and doesn't need to measure the second qubit. And here she measures sigma x on the first qubit and sigma z on the second qubit, okay? Now, each of these measurements, the result is either +1 or -1. She takes the product of +1 and of whatever she gets, and this is how she fills the first row.
but
And
she
similarly,
doesn't.
yes, Joanne. Mhm.
You mean that she does in advance?
What do you mean by advance? No.
But
Alice and Bob, no, they don't do it in advance. Alice and Bob first agree on a table, like the table sitting here. They make a copy of this table, put it in their pocket, and go to the room. And when they go to whatever room they go to, they take with them in a bucket 2 qubits. Alice takes 2 qubits and Bob takes 2 qubits. In her room, Alice has a lab which allows her to measure the 2 qubits. She can measure sigma x on the first qubit or sigma y or sigma z on either of the 2 qubits. And once she is given a row, she makes the measurement stipulated by the row. So for example,
but
if
she
she's
doesn't.
given,
But you said she doesn't know what row she's given.
she knows what row she is given after she goes to her room. Then she's told, fill for me the second row.
But that's not what I thought. That the rule was that they wouldn't know what row they are given.
They don't know a priori, but they do know after they are separated. So Bob has no idea what row Alice is given, and Alice doesn't know what column row was given. But of course, each one of them knows what row or column they have to fill.
Well, that was not clear. I thought initially they were not told which row or which column, but you say they are told.
They are told, but only once they are non-communicating, incommunicado.
Okay.
Okay, so they are not allowed, Alice is not allowed to tell Bob, I was asked to fill row 1.
But she knows that she has.
But she knows she has to fill row 1.
Okay, thank you.
Okay.
Sorry, Yossi. Do they pick up independently a 2 qubit state, or is it the same qubit state that Alice and Bob pick up?
So the way it works is like this. Before they get separated, they prepare a quantum state, which I've not yet specified which quantum state. They will prepare a quantum state of 4 qubits, which is entangled. Now, Alice will take 2 qubits to her room, and Bob will take 2 qubits to his room, and they will perform the measurement according to the table on their qubits. Did this answer your question?
Yes, but then once, say, Alice makes her measurement, this operates a projection on Bob's qubit.
Of course, yes.
And so
Yes.
it's not clear. Okay.
So, so it's a miracle, so I have to explain it. You're right. But basically, the point you are raising, this is the issue that is going to be responsible for the fact that on the intersect, they measure the same thing.
Okay.
So the measurement of Alice will in fact prepare for Bob a state so that his measurement will be consistent with hers on the intersect.
your point is no matter what it projects onto, the consistency condition will be fulfilled.
That's right. The miracle of this, the wonder of this table is that the consistency condition will be fulfilled no matter which row or which column were given to Alice and Bob. So there is something magic about this. This is why it's called magic square. But I've not yet described what states Alice and Bob are going to use. So far, I just described what table of measurements they agree on.
Good.
So if
Thank
it's
you.
okay, if it's clear, I'll continue.
Excuse me, may
Yes.
I ask a question? Just I'm lost. What does it mean measure? What means what is measurement in your setup? I'm lost with this term.
For example, for the first row, Alice and Bob make two Stern-Gerlach experiments, right? On the first qubit, she aligns the magnet in the X direction, and for the second qubit, she will align the Stern-Gerlach with the Z direction. Is this good enough? She needs to go to a lab. This I didn't make clear. She will need a fancy lab to do this measurement.
Okay, so it's a little bit, the rules are a little bit more different from the original rules. So they have a partial access to information, right? So they can measure something. That's what you state.
Yes, they have access to a lab, but they are not allowed to, right? They are incommunicado. They are not communicating.
Sure.
Okay.
Right.
Okay, so good. So now let me try and explain where would the miracle that Alice and Bob will fill the intersect with the same entry. So you see, since Alice and Bob use the same table of measurements on the intersect, Alice and Bob will measure the same observable on their qubits. So for example, if the intersect is this BJK, both Alice and Bob will measure the same observable on their qubits. Now, how can we pick a state for Alice and Bob so that they will agree on this intersect? Now remember that the BJK is a binary observable. So the result of the measurement is either +1 or -1. So we want Alice and Bob to prepare a quantum state of 4 qubits, which has the following property, that it's an eigenstate of the measurement BJK for Alice and the same measurement BJK for Bob with eigenvalue 1. So how can, if psi AB is a solution of this eigenvalue equation with the same observable for Alice and Bob, and each observable is binary, so I could get here plus either if both Alice and Bob get plus, or if both of them get minus. If one of them would get plus and the other one would get minus, this would not satisfy this equation. So Alice and Bob have to prepare before they, as part of their strategy, Alice and Bob have to prepare before they go to their separate rooms, a quantum state psi AB, which is an eigenstate of this BJK, the same B for all 9 observables in this table, okay? And they will win if I can find such a state, psi AB, which is an eigenstate of all these 9 equations. So it looks so here it just states that if both of them get 1, then I satisfy this eigenvalue condition, and if both of them get -1, I satisfy this condition. And it appears at first as if I get 9 equations. It turns out that 9 equations are too many equations to find a psi AB if they were independent. But the beauty is that you don't need the 9 equations. It's enough to satisfy this equation just for the green square. Because as I explained before, the green square, determines the entire table. So the equations you get from all other entries are actually follow up from the equations from these 4 entries. So now we have to solve this equation bjk psi ab for these 4 observables that sit in these four corners of the square. Now there are 4.
You see,
Yes.
does it matter that it's a square? If it were only 4 of the 9s, would it matter if it were not a square?
Well, the reason I picked the square because this was how I constructed the rest of the table. But I could pick, for example, instead of this square, I could pick a square here. I could pick any other square.
No, but
I need
not a square. Take 4.
no. Then I don't know how to do this. I know how to do it with a square.
Okay.
And the point is now that we get 4 equations, right? For every point in the square, there are 4 equations for this psi, which is a state of 4 qubits. And this is just the right number of equations I need to get a unique solution psi AB. And it turns out, if there will be enough time, we can do the algebra and find out that psi AB is actually a product of 2 Bell pairs, where here is a Bell pair. It's a superposition of the state 0, 0 plus 1, 1. So this is also the state used in the Einstein-Podolsky-Rosen thing. And what Alice and Bob need to prepare are 2 such Bell pairs. Am I clear so far? So now you see that if Alice and Bob have a product of 2 Bell pairs, they are guaranteed by this equation that on the intersect they will always agree. So we showed that we will win the game always. So because in a Bell pair, Alice qubits are perfectly correlated with Bob's qubit. I think this was one of the remarks of some of the questions that was raised before. So Alice shares with Bob Bell states, and this will guarantee that whatever, there will be perfect synchrony between the measurement of Alice and Bob. How am I doing with time, Joel?
Well, you got another 10 minutes, 12 minutes.
Okay. Good. So now here is an interesting thing about the measurement of Alice that I want to point out. You see, Alice is going to perform measurements on her qubits, 2 qubits. Each qubit is a part of a Bell pair. Now, if you ask as far as the measurement of Alice is concerned, it's enough to look at what is the density matrix that Alice possesses, right? Because she's going to make measurement on her qubits. So the outcome of her measurements are determined by partial tracing over Bob's qubits, because to these qubits she has no access. Since Alice and Bob share Bell states, which are fully mixed, if you partial trace over Bob, the state of Alice is the fully mixed state. And therefore, Alice is making measurement on fully mixed states. And because she's making measurement of fully mixed states, the outcome of the measurement are completely random. They could be +1 or -1. So for example, if Alice would be given this second row, the outcome could be, say, -1, +1, -1, and we know, and there is a constraint that the product of the 3 entries in a row has to be +1, because this was how this table was constructed. So now here is something interesting. You see, the row is filled randomly, but once you measured these 2 entries, which are random numbers, the third random number is completely determined because there is a constraint on the product. This is what people in Foundation of Quantum Mechanics called contextuality. The result of a measurement is dependent on what other commuting observables were measured with it. So perhaps I'll come back to contextuality later. I don't know if now there is a subtle point here, which I want to explain. You see, for example, a measurement of the first row is of the observables in the first row is easy because as you can see, the first qubit is measured in the x basis, and the second qubit is measured in the z basis, and here you don't need to make any measurement. So the first row seems to be easy, and this is also true for the first column. It's also true for the second row and the second column. But it looks more tricky if you look at the, say, the third column. You see, in the third column, the first qubit, sometimes here you see sigma x, here you see sigma z, and here you see sigma y. You can't measure sigma x on the first qubit because the measurement of sigma x on the first qubit will interfere with the measurement of sigma z on the first qubit. These measurements are not non-commutative. So it is true that this observable, which is sitting in this square, commutes with this observable. But it commutes because the first term anti-commute and the second term anti-commute. So even though we tell students when we teach them quantum mechanics that commuting observable can be measured, the question arises, how do you perform in practice a measurement of these 2 observables? They are commuting, so there must be a way of measuring them simultaneously, but the simultaneous measurement is not going to be a simple measurement of the first qubit and a different measurement on the second qubit, because these measurements are problematic. So the question is, how do you measure commuting observables? It's true that this observable commutes with this one, but how do you measure it? You can't measure on the first qubit and then measure on the second qubit. You must do something more sophisticated. Now, I'm not sure, Joel, how am I doing with time? I'm not sure I will have enough time.
You got 10 minutes.
I'll got 10 minutes. So I'll tell you how to measure this. But to do this, I need to introduce a notion which is called these quantum circuits. And if you're not familiar with this, it's not, I don't know if this is going to be completely comprehensible. So I'm going to represent qubits. Oops, sorry. The qubit is represented by a line. So here, for example, is the qubit 1 within a state 1. And here is another qubit in a state 0. I can take the qubit in a state 1 and operate on it with a unitary 2x2 matrix, which is the Hadamard matrix. And I can, on the second qubit, I can operate with another unitary, say, sigma z, which is a unitary operator. The other thing I can do with 2 qubits is do a controlled measurement, which is a unitary, and the controlled measurement is described here. If the first qubit is in the state 0, I do nothing on the second qubit. But if the first qubit is in the state 1, I flip the second qubit. And So the matrix H is a linear combination of sigma z and sigma x, and it interchanges the sigma z with sigma x. So this was just a preliminary on quantum circuits. And the way to measure, for example, the parity B of the two qubits here is going to be like this. So since B is a binary, so it has eigenvalue +1 or -1, I can write it as B plus minus B minus, where B plus is a projection on the plus eigenvalue, and B minus is a projection on the minus eigenvalue. Since these are projections, the square of B plus minus is the same as B plus minus. And now what I can do is the following thing. I add another qubit to the game. This is how I'm going to perform the measurement. I'll call this extra qubit, which is initially in a state 0, an ancilla. And I measure the parity of the product of the two qubits in these two rows. I measure it on the ancilla. So this is a unitary. The unitary record the joint parity on the ancilla, and it is made like this. If the B plus, here I'm interested in the parity of B and B prime on the two qubits. So I took the plus plus and minus minus, and then I don't change the parity of this, because plus times plus and minus times minus give me plus. But if I have plus and minus a plus, I flip this ancilla qubit, and therefore it changes the sign. So the nice thing I did in this operation is that I measured the product of the parity, but I gain no information. I do not learn anything about the individual parity of the two qubits. And in this way, I can realize the measurement of commuting variables, even though the individual terms don't commute. I'm not so sure that I got this through.
Maybe
now,
you could give some references.
Well, okay, so for example, here is in practice how you measure the product of parities of these two qubits. You put two C0 gates. You see, if both of them are 0, if this qubit is 0 and this qubit is 0, then this C0 does nothing, and this C0 does nothing, and the measurement of the ancilla would give me 0, which means that the parity was 0. If this is -1, if this is +1, and this is +1, then this would flip, the first qubit would flip this to 1, and this would flip it again from 1 to 0. So if both of them had parity -1, I again read 0 on the ancilla. But if one of them was 1 and the other one was 0, only one of them would flip, and I would, by measuring this third qubit, I would learn about the product of their parity. Okay, so you can, so this just describes how you measure the parity of sigma z tensor sigma z. Similarly, you can measure sigma x tensor sigma z, and these were the observables that we were concerned before. It's not clear to me that this is, I'm not explaining it sufficiently clearly for this to be absolutely clear, but I think it represents the idea that in fact by adding ancillas you can measure the parity. And in the case, for example, that Alice wants to measure this row where there is both sigma x, sigma z, and sigma y, she needs two ancillas to record the two parities. And the two parities would allow her to fill that she will get two integers to fill this entire row. So she will fill this square, and this square will be the product of the results. I have a feeling that I'm not doing a very clear job of explaining this.
But why don't you stop and open for questions and maybe give what's a good reference?
Oh, good. But I definitely welcome questions.
Well, let's first of all unmute yourself, and thanks, Yossi, for a most interesting talk. And then why don't you stop sharing?
Let me before I stop, let me just say something about concluding remarks. So Mermin and Peres did not invent the game, but they invented the square, this magic square, to give a simple proof of the Koch-and-Specker theorem, which I'm not going to describe because I don't understand it myself. And their main interest in Koch-and-Specker and the point where, or at the beginning, the main interest in this magic square was because it's an example of the issue of contextuality of hidden variables. As we saw, if you would like to interpret to replace quantum mechanics with the hidden variables, you would have to invent hidden variables that also care about contextuality. As I explained, filling a row, you would get random entries, but in two of the random entries would determine the third random entry. So this is the notion of the hidden variables would have to be contextual. They would have to know not just how you prepared the system, but what kind of measurement did you make. Now, this issue of quantum games, and in particular this Mermin-Peres magic square, is now used in computer science as this is the simplest and perhaps a paradigm for what they call a multi-prover interacting proof system with entanglement. This is the acronym for multi-prover interacting proof is MPI, and the star means that you're allowed to use entanglement. And one nice reference for various quantum games is this paper, which is noted here by Kleeb, Hoyer, Toner, and Watrous. And now I'm done, and I'll stop sharing.
Okay, thank you again. So there was some question.
Give me hard time.
A question is in the chat. Anybody wants to ask a question? I think the chat was asking if this can be generalized to larger.
I think this is a wonderful question. I don't know of a generalization. There are various generalizations one may want to consider. For example, you could consider a generalization which involve more parties, not just Alice and Bob, but Alice, Bob, and Charlie. And you could consider generalization which would involve, instead of having a 3x3 magic square, one would have 4x4, or perhaps a rubric cube of a three-dimensional cube. And there are many directions one may want to generalize. I don't know of any such generalization, and I think it would be delightful to investigate this question, but I don't know that it has been addressed. At least I've not seen it being addressed.
Are there any other questions or comments?
Yes. If Alice wants to build the apparatus to make these more complicated measurements that you've described, roughly what sort of components would she need? Complicated arrangement of Stern-Gerlach magnets or something else?
Okay, I like this question. So my interest in this Mermin-Peres game started in a project that I gave to students here at the Technion, and I wanted them to realize this game on one of the existing quantum computers. So you can take there are many quantum computers now available on the cloud, which are accessible, and you can realize the quantum computers are physical systems, and you can program them so that they will execute this this magic square game, and the realization is closely related to the circuits that I tried to show to you with the ancilla, where the measurement is made with an ancilla. So basically, you would need this C-NOT gate, with controlled NOT gate. This is in a quantum computer. This is a primitive that you can use. In practice, it's a term that describes interaction between qubits. I don't know if this was sufficiently clear answer to your question. So you can realize them on quantum computers, which would mean you can realize them on superconducting qubits, and we in fact realized them on quantum computers made from a string of ions. It was amusing and interesting that when we ran this experiment on the quantum computer, the success rate was not 1, because the physical system makes errors, but it was something like 0.99. You know, we won the game with very high probability, much higher than 8/9. So these experiments at least prove that quantum mechanics is not wrong.
Thank you.
Yeah. Will you allow me to ask a primitive question, if you don't mind? My primitive question is this. Suppose if you assume that Bob and Alice their brains are macroscopic quantum states, and then they will also be entangled if they start from the together. I mean, if they were at some historical event, they were together. So brain will also be entangled, and then you don't need all this quantum bit of exchange, and their brains are entangled, and they can just convey the information through entanglement of their brains.
You know, I think I will only make the following comment, that when Alice and Bob make this game, they need to make a preparation. In the case that I described, they prepare the quantum state. Now, the preparation of a quantum state, in some sense, the process of preparing a quantum state disentangles the state from the environment. Or to say it more precisely, the preparation of a quantum state prepares a state which is in a product state with the rest of the world. So this is part of the art of preparing a quantum state. So in order to play this game, for every round of the game, Alice and Bob need a fresh pair of entangled qubits. And they prepare this fresh pair of entangled qubits, which means that they disentangle them from the rest of the world, and in particular from their own brain. Now, with respect to your suggestion, I'm not sure what kind of preparation would you propose for Alice and Bob to do if they want to use their brain as their quantum system. I'm not sure what you are proposing.
My question was actually, I mean, because your talk was on entanglement, and my question was related to entanglement, not exactly to your game. It was basically, can our brains, which if we can describe them as macroscopic quantum states, be considered as entanglement? And then probably on that basis, we can explain those ideas of telepathy and all that. That's all my question is.
let me only make the following simple comment, that entanglement is known to be a very fragile quantity. So it's very easy to, if you make an entangled state and you couple it weakly to the environment, or you lose some information is being leaked to the environment, the entangled state is effectively replaced by a mixed state, which has no interesting entanglement. So one of the big challenges of present day technology is to build complicated many-body quantum states with entanglement that can be sustained for sufficiently long that we can do something with this. I think at the moment, doing it with the brain is a challenge, is a serious challenge.
Okay.
Perhaps for the better.
Are there any other questions or comments? If not, then let's thank Yossi again for a very challenging talk.